Okay, okay. It's coming interesting one, which in regard to high-speed test. Malech has 30 years in various engineering design, sales, and marketing roles in both ATE and semiconductor companies. Okay, let's see what he will let us know about high-speed serial testing.
Hello, I'm Doug Malech, Technical Marketing Engineer at MultiLane. I'm here today with Choung, Senior Application Engineer at MultiLane. MultiLane supplies the data communications industry with high-speed test and measurement equipment. Today, Choung and I are going to talk about how external high-speed instruments can enhance loopback testing of 400 gigabit and 800 gigabit Ethernet high-speed I/O devices in a production AT environment. Loopback testing involves looping the device's transmit output directly back to its input to test high-speed serial I/O. However, with new devices coming out with 56 gigabaud PAM4 data rates, our customers are seeing a greater need to better visualize the device's transmit and receive characteristics. External high-speed instruments can be used, but engineers may not be familiar with using high-speed external equipment in a production environment. In addition to the reasons just mentioned, external instruments provide additional benefits. For example, a common set of external instruments allows all devices to be tested against a common reference. During loopback testing, the device is testing itself, as shown in the top right picture. As a fab process drifts, devices will still pass loopback, but there will be no way of knowing that the parameters are drifting over time. Knowing early on that a process is drifting can help to report back to the fab house to correct a problem before it causes devices to start failing. For engineering characterization, having better visibility into parameters like eye shape and frequency response can help to improve the design. Test flows can be modified as more becomes known about the device's behavior. Field failures can be debugged on the AT platform, and then the tests to prevent future field failures can be immediately implemented on the production test flow. And finally, there are devices like PCIe, USB, and HDMI that do not have pairs of transmit and receive paths to connect into a loopback test mode. The outline for this presentation is as follows. First, we will explore some of the test engineering challenges at these higher speeds. Then we will explore some high-speed instruments and components that can be used by you in the AT environment. Third, we will show the viability of these methods through some examples of high-speed measurements using production ATE instruments running inside an Advantest 93000 tester. There are challenges at higher speeds that must be addressed for an ATE implementation to make sense. Of course, the number one metric is for the implementation to meet the performance needs of the device under test. The high-speed option must be integrated into an existing tester platform in order to take full advantage of a typical production test flow. For example, direct docking must be maintained for both probe and package test solutions. We must also keep test time down to keep this AT solution cost-effective. And finally, time to market is very important, and then we have to minimize test program development. As stated in the last slide, the most important item is that the AT implementation meet the performance criteria. As a quick reminder, 400 gigabit Ethernet and 800 gigabit Ethernet lanes are actually individual 4-level wideband signals operating up to 112 gigabits per second. The industry also refers to these 4-level signaling protocols as 56 gigabaud PAM4, and the signals have a Nyquist frequency of 28 gigahertz. Think of double data rate RAM operating at 2666 gigabits per second, and then the clock frequency is 1333 gigahertz, or half the data rate. It's the same here, where the symbols operate at 56 gigabaud, and the Nyquist clock frequency is 28 gigahertz, or half of 56. As you add components in the path between the DUT and instruments, the frequency content of the signals can be severely attenuated. The goal is to source a signal with desired characteristics at the DUT input and to recreate the DUT output characteristics at the measuring instrument. In order to do this, my crude drawing shows how the source instrument must add preemphasis to compensate for the path's signal attenuation. Likewise, the measuring instrument must provide postemphasis to recreate the DUT transmit output signal. We'll show later how this is done. In order to accomplish these performance challenges, the following can be done. We can place the high-speed instruments close to the DUT to minimize path distances. We can design the hardware and software to provide reasonable test times. We will choose PCB materials with greater than 40 GHz capability. We'll also choose a suite of components like BISTs, splitters, and RF switches that also operate well above the Nyquist frequency. Finally, the source and measure instruments have to compensate for the frequency losses through all of these components in the high-speed path. Here's a picture of the multi-lane high-speed AT solution working inside the Advantest 93000 test head. The high-speed instruments are inside a frame that resides between the test head and the wafer prober. This way, the instruments are within a 20 centimeter cable length, coax cable length, from the DUT. All of the direct docking, software, hardware, and mechanics are taken care of by the Advantest 93000 because the high-speed instruments have been fully integrated into the test head. This feeds back into what we said to minimize the distance between instruments and the DUT. It's being crucial to better performance at these high speeds. This is a picture showing the multi-lane twinning frame without the load board attached. You can see the short isolated cables coming from the instruments on the right-hand side of the picture. There are up to 16 differential transmit and receive channels in this cavity. The empty cavity on the left side of the picture can accommodate an additional 16 lanes for a total of 32 lanes of high-speed source and measure instrumentation. That's 32 channels of source and 32 channels of measure. The 93000 tester resources come up through the 16 smaller cavities on the perimeter of the twinning frame. The picture in the lower right shows the multi-lane twinning frame docked to the 93000 test head without the DUT load board attached. Here's a block diagram of the high-speed signal path. We are also showing the various devices that might reside on a high-speed load board, such as BISTs, wideband splitters, and RF switches. When the DUT load board is docked to the twinning frame, line bait connectors are engaged into the multi-lane high-speed instruments. This way, most of the path from the DUT to the instrument cassettes is through high-speed coax cabling. The coax cable connections near the DUT are shown on top, but there are ways to have the cable connections as well as all of the high-speed components reside on the bottom side of the load board. In order to maintain reasonable test times, you can keep the test time down, and you can also test more parts in parallel. The multi-lane high-speed option on the 93000 tester has 32 high-speed channels. For example, this is probably enough channels for quad-site transimpedance amplifier testing. The Advantest Smart Test software facilitates going from a single-type test program to a quad-site test program with minimal software overhead. If 32 sampling scopes are installed, all 32 scopes can measure in parallel. Then, while a second set of samples are being taken, the computer can be post-processing the data from sample set 1, as shown below. This improves test time as well, since you don't have to wait for post-processing to complete before initiating another sampling period.
Hi everyone, this is Choung. So one of the most important points in AT testing is actually the test time. So at MultiLane, we really understand this and we really minimize the conflict times of our instrument as well as maximize the throughput of the measurement. For example, as you can see here for the BERT, the setup time is for 24 milliseconds. This is actually just a one-time process for all of the lanes on the BERT. For BERT, it really depends on how long you want to run it. Here we actually do it at 1 second. And it takes around 80 milliseconds for the measurement time. Again, this is the real measurement of how long it takes for one actual measurement. done on the SMAC test. So in 1.5 seconds, you can get the BR measurement of all 4 channels. So if you have a quad channel devices, it takes just 1.5 seconds. Now let's move on to the scope. Our scope actually has the FPGA base, deep memory, and you can probably think that it may take a little more time. Indeed, it takes 2.2 seconds for the setup time. This may be a little high for you in the AT world, but what we have is that we can do all of the DSP and processing of the raw data in the background of the SMAC core while taking the next measurement. As you know, the V90K has been around for a while, and the SMAC test environment is very mature. So to make our implementation to the tuning frame as seamless as possible, we actually have the API for our instrument, which is fully compatible with the SMAC test environment. And you can just do the call of the order command directly from the SMAC test. We even have some basic test flow available already to the user. So this will make it very easy for you as developers to do from a single site and then just copy it for multi-site testing. Another key point is that you can do the program developing of the instrument in an offline mode, which is you can remove the tuning frame with the instrument on it and work on your program, because our instrument will have its own table for the power and then the Ethernet. So you don't have to utilize the time of the tester. The last point is that the SMAC test will also do all of the data logging and communication with anything else, including the handlers, the propellers, etc. And for the data logging, you can see it in the next slide. I'm going to show you that. So here is the capture of the analyzer tool of a 56 gigabaud PAM4i and a 56 gig NOC done on our DSO, our electrical sampling scope. From down below, you can see, the text is actually the measurement. All the measurement, you can see the levels, the eye height, the eye width, or even the eye amplitude of the PAM4i and the NOCi. And with data logging, you can actually set the minimum, the maximum, and the threshold for the pass-fail criteria very easily. For example, if you have a part, you can test like 100 or 1,000 parts and find the average, and then based on that, you can determine these pass-fail values. Another note is that what's good about this is that with our DSO, we provide all of the PAM4 and NOC measurement library for free. For example, for those of you who have the DSCA in your lab, right? For any filter, any license, you got to pay for it. So this is a very good advantage of our instrument. Next, I would like to show you that capturing 1 gig on the AT setup is feasible, and we can do it by running you through an experiment that we did. So for 1 gig PAM4, this is really done by doing a 56 gigabaud with PAM4 coding, and the Nyquist of that's actually at 28 gigahertz. So for the components, we got making sure that the bandwidth of it can be minimum 35 or 40 gigahertz. And all of this actually available in the market right now. For example, as you can see here, for the BCBA material, we use 50 gig Megatron 6 laminate. We have BIST, we have splitter, and we also have switches. First of all, let's talk about feature of our instrument. We have different burst family supporting different libraries, but in general, our transmitter side support all of the standard BRBS patterns from 7 all the way to 31Q, including BRBS 13, SFPOQ, and even U35 pattern. For the ability to adjust the eye or doing the optimization signal shaping of the eye, we have 3 and 7 tab FFE base. The 7 tab FFE is really what makes the 1 gig possible. Because at this library, 1 or 2 dB will actually close the eye. So with this, it allows us to compensate or optimize for the loss of the cable or any channel path from the BERT transmitter side to the DUT input. We also have polarity inversion or even error insertion if you really want to test your error detector. On our error detector, measurement-wise, we can do histogram, which is the distribution of the levels, 4 levels or 2 levels of the estimation of the SNR, signal-to-noise ratio, and the BR. For 1 gig link, equalization is very important to maintain a reliable link, right? So we support different kinds of EQs, including adaptive FFE, which can go up to 50 taps, DFE, or even reflection canceller. On the DSO side, we actually have very low intrinsic jitter, 200 frames per second, again with very low noise that allow us to measure accurately the 1 TB PAM4i. We provide very fast acquisition and deep memory because we have the FPGA inside. As I mentioned earlier, we have full measurement library for the eye. For pattern log, we can support up to BRBS 16, or for PAM4, we can capture up to SFPRQ. We support all of the standard filters, including DFE, FFE, CTOE, and one key filter that makes the 1 TB feasible is the de-embedding. To compensate for the path and to trace what is the signal out of your DUT output, which we will explain more in the later slide. Here is a picture of the test trace on a DUT board that we built. We want to use this to show you that we are able to design the PCBA trace with very minimal loss. For example, here we have a 1.5 inches or 38 millimeter. The incident loss is less than 2 dB at Nyquist. Here you can see the vertical lines actually pointing at the 28 GHz for the Nyquist. Here you can also see the return loss. So one rule of thumb for design a 1 TB interconnect is that as long as the return loss is below -10 dB, then we are good. On the left side, you can see a stacked up view of the PCBA layers. Of course, we want to use the best material out there, right? For example, like Megatron or the Roger. Next is the BIST. With our solution, you are not only be able to test the DC component of your signal, but also the high speed as well. We say like we do high speed testing. Here is an example of the insertion loss and the return loss of the BIST that we use. Here's a more example for the splitter. This is the knowledge splitter. This is actually the measurement, not the simulator, by the way. And this is for the 1x2 OF switch. Again, the return loss is below -10 dB, which should be all good. Now that we have reviewed the S parameter and the performance of the components, so let's put this into use. So for testing config, we have two possible configs right here. The first one is called the sample loopback. This is the same as the traditional external loopback config to test your DUT. However, by using the splitter from your DUT transmitter side, it allows us to actually still keeping the same loopback testing that you have been doing, but at the same time, we can see what the signal looks like by samples on our scope. Again, this is a good config, especially for debugging purpose, of your parts and even production, because it really provides you one step further to characterize your signal at the same time. The other config is testing using our BERT and the switch. For example, here you can see the DUT transmitter side is going to our BERT error detector, and we have the switch here. So if you can switch it to the receiver of your parts and do your measurement, or you can do it on our BERT. Or with the switch below, our transmitter side can connect to your error detector, and we can do the BERT on your parts. So really, with the two configs, you can do a lot of combination, and you can mix and match, but you can select the most appropriate config for your testing need. With the current implementation of our instrument in the twinning frame, we can support up to 32 channels, including the transmitter side, the error detectors, and also the sampling scope.
Here's an example of a load board measuring 112 gigabits per second PAM4 signals through a splitter. The splitter output goes to a 50 gigahertz sampling scope and a 56 gigabaud PAM4 BERT, both at the same time, both inside the twinning frame. For a production test example, the 20 centimeter coax cabling would be secured under the load board inside the twinning frame to prevent it from moving around and from being damaged. We just have it on the outside for demonstration purposes. Both the sampling scope and the BERT have a combination of front-end analog and digital techniques for de-embedding or compensating for the high-frequency attenuation through the path from the DUT to the instruments. Here we're showing the effects of high-frequency attenuation in the path from the DUT through the splitter to the DSO. A clean PAM4 signal leaves from the DUT transmit output. This is the top right PAM4 picture. The attenuated signal reaches the DSO and is sampled. The sampled signal appears as if the PAM4 data eyes have disappeared. If the story ended here, we would be failing this device. However, using various techniques to compute the frequency loss characteristics of the DUT to the DSO through the splitter and coax cables and blind mate connectors, the DSO recalculates the pre-distorted signal and reports this de-embedded signal to the smart test software. The signal in the lower right is the recreated signal, and then we are doing our pass-fail criteria on the signal as it appears on the output of the DUT. On our demo board, we measured through the BERT and the DSO in parallel to reduce test time. The GUI lets the test engineer visualize the results of the BERT and the DSO instruments. The BERT results shown in graphical form on the left and the DSO results on the right. In conclusion, we recommend keeping simple loopback, but adding performance with external high-speed instruments for 112 gigabit per second PAM4 test coverage. By the way, we're using 56 gigabaud PAM4 as our primary example in this exercise, but there are other high-speed protocols operating at similar speeds. Our instruments can be used for testing the physical I/O of all of these high-speed protocols, including Ethernet, PCIe Gen 5, Gen 6, USB 4, and others. We recommend leveraging industry-standard hardware, software, and mechanical production package probe testers. This way, adding high-speed test doesn't compromise all of the other great tools provided by the Advantest 93000 tester platform. Place high-speed instruments close to the DUT and choose source and measure instruments that can compensate for the path's high-frequency attenuation. And finally, use high-speed load board materials, BISTs, wideband splitters, RF switches. With these components, you can do most of the high-speed routing required in your application. Choung and I hope you enjoyed the presentation, and our company is available to help you successfully enter this new high-speed market space. Thank you.
So thanks for a fantastic presentation from Doug and Choung. We got one question from the audience, Jose Moreira. On the presented measurements, what's the signal path, test feature loss, or signal traceless?
Yeah, so the question is what's actually, the signal path for the measurement we saw. This is actually in slide number 23. So Doc can put up at the same time I can explain. What we have is we have a 1 gig quad channel device, 30 or ASIC on the DUT. This will have like 1 or 2 trace route into the 40 gig splitter. From the splitter, you have the connector, like the 2.4, 1.85 millimeter connector. We connect that one using the cable to our DSO instrument. So roughly you have 6 dB, right, from the splitter, and then 20 centimeter cables. So roughly the whole part is about 10 dB. And at 1 gig, right, 1 or 2 dB loss is enough to close the eye. But we will be able to get to recover the eye by using the embedding. So what we do is we can measure the S21 of that path. And then we use that S21 or S2P file to de-embed the channel loss to really recover the signal by going to that lossy path to really show you what's the eye looking like right out of the DUT output, at the pin. Okay.
Okay. The next question is from Albert Su. Using backdrill or bright via for 122 gigabit length.
Yeah, this is a very good question, Albert. Thanks for this, and especially in the previous section, as you heard from Khalid, right? He talked about simulation of 56 gig. Now we're doing 1 gig, so this is even more difficult. So you see for VIA, 56 gig, so it's okay. There's some debate there, but you see for 1 gig, that cannot be done. So really, we have to have the signal route to the top of the PCBA using the microscript, really high quality trace. And again, I want to emphasize this: simulation for 1 gig is really important, right? Before you actually do everything, step and everything, you have to done just simulation first. because for 1 gig, a small impedance mismatch, right? Between, for example, for 45 ohms, 48 ohms, that will definitely have a penalty on your I measurement, and also the BR also. Yeah.
Okay. Any more questions? Okay, I want to ask one. Can multi-lane instruments be used to calculate S21 of path from DUT to instrument?
Yeah, the answer is yes. So there is one unique, technology and architecture about our DSO, which is we do the S21 in time domain, where we capture the I. Based on that, we can do the S21 in time domain. And actually, we do the FFT from the time domain, then we get it in the frequency domain. So you will ask, how do I do the S21? Is it, a frequency sweeping? No, we're not doing frequency domain. We do it in time domain, and then FFT to get to the frequency domain.
Okay. Okay, so there's no question from the audience. Okay, so thanks again for a nice
one more question. Somebody asked whether the D-embed could really remove the influence of the test system, such as the PCB and socket. They asked it in the WeChat group. So
sure, this is a very good question. Let's go back to slide number 24. I think it's the next slide. So
and especially in terms of crosstalk, yes.
Sure. So let me start doing this by doing the following. Yes. So the IR of the DUT is cleared, right? After you go to the channel path, after you go to your test setup, in most of the case where customer do external loopback. So really you have a looping back trace it from the TX to the RX of your DUT. Then the signal going to the receiver of DUT is actually close. So with our DSO, right, we have the embedding. What we do is we measure to one of the channel path, and then we de-embed it. Again, this is compensation for the insertion loss, not return loss. Actually, we can do it if your return loss is below -10 dB. In that when we can do the compensation, we can deal with it, and we can recover your I, the 1 gig I. But anything getting work, then we cannot do it. That's why doing the side is very important, and choosing the best interconnect around there is a must. Yeah. Okay.
Thank you.
Okay.
Do you want to add anything to that? Are we good?
We're all good. Thank you very much, Choung, for answering those questions.
No problem.
Okay, thanks again for the fantastic presentation and the Q&A.
Thank you, Kenny.
Thank you.
Yeah.
Thank you.
We want to thank our sponsors once again, Test Tooling Solutions Group as our premier sponsor, JDT Technology, our honored sponsor, our distinguished sponsors, Nidec SVTCL, Smiths Interconnect, TSC, and Feldman Engineering. And a reminder that you can reach out and contact them through the website, through the chat or message buttons there. So please take a moment and thank them and reach out and ask them about their products and services. I'm sure they will be very happy to help you. And also I want to thank our media partners, ACT with Silicon Semiconductor China and EE Times with an upcoming Double Summit event next month. So you can find links to this on our website. And then an extra special thank you to Test Tooling Solutions Group being our premier sponsor. Certainly a lot of innovative solutions there in this space of test equipment and test consumables. So please thank them once again. And lastly, I would like to thank all of you for participating in TestConX China. It's been a great pleasure. I'd like to thank the authors and the committee, but most importantly, thank you for joining us. We hope that you found this to be informative and useful, and certainly appreciate any feedback you may have. We look forward to seeing some of you at TestConX in May in Mesa, Arizona, and then TestConX China 2021 in the fall in Shanghai again. So Thank you. Have a good rest of your day.